In the cells of our body, we have many different types of biological processes that are catalyzed by enzymes. And what these enzymes do is they speed up the rates of these biological reactions. Now, because enzymes affect the rates, to actually understand how enzymes work, we have to understand the rates of these enzyme-catalyzed reactions. And in fact, enzyme kinetics is the study of the rates of these enzyme-catalyzed reactions that take place inside our body. Now, in the next lecture, we're going to begin our study of enzyme kinetics. But in this lecture, we're going to remember some basic information about how to actually represent and express the rates of chemical reactions. We're going to remember what the rate law is and what the rate constant is and how enzymes affect these two quantities. And we're also going to remember what the order of reaction is. So let's begin with the following hypothetical chemical reaction. We have reactants A and B that are being consumed, and C and D, the products, are being formed. Now, because we have a 1:1 to 1:1 mole ratio, because the coefficients are 1:1 to 1:1, and because these are being consumed, and these are being produced at the same time these are being consumed, these four equations basically describe the rates of these individual reactants. So as the reaction is progressing from the reactant side to the product side, A is being consumed, and that's why the rate of A is negative, and the rate of A is simply given by the change in the concentration of A with respect to some time interval. And likewise, B is also being consumed, so the rate of B is negative, and it's given by delta, the change in concentration of B with respect to the time. And likewise, over the same time interval, these are the rates of C and D. So the rate of C is the change in C with respect to T, and the rate of D is change in D with respect to T. Now, these equations aren't very useful. What we actually want to be able to express is the entire rate of that entire equation as a whole. And this is where the rate law and the rate constant comes into play. The rate law basically uses the rate constant as well as the concentrations of reactants to basically express mathematically what the rate of that chemical reaction is as a whole. So let's suppose we have the following elementary reaction. So what do we mean by an elementary reaction? Well, recall from general chemistry, an elementary reaction is a reaction that takes place in a single step. And the important thing about elementary reactions that you have to remember is, in any elementary reaction, we can use the coefficient of that reactant to basically determine what the order of that reactant is within that rate law. So we can use the coefficient in front of the reactant to basically tell us what the exponent value is of that particular reactant in that rate law. So the rate law of the above elementary chemical reaction is usually described by using the rate law, and the rate law depends on the rate constant K and usually depends on the concentration of the reactants. So in this lecture, we're only going to look at elementary reactions, but you have to remember that if we're dealing with a multi-step, complicated reaction, then we cannot simply use the coefficients. In that case, we have to determine the rate law experimentally. But if we have a single step reaction, then we can use the coefficients to calculate the rate law. So in this particular case, going from A to B, A is the reactant and B is the product, and let's suppose the rate constant is K1. And that means the rate law for this reaction is given by, so the rate of the forward reaction V forward is equal to K1 multiplied by the concentration of A to the power of 1, because the coefficient here is 1. If this coefficient was 2, then this exponent here would be 2, and so forth. Now, if we go in reverse, then the only thing that changes is this becomes the reactant, this becomes the product, and so we replace the concentration A with concentration B, and we replace K1 with K minus 1. And remember that if this reaction achieves equilibrium, then the rate of the forward will be equal to the rate of the reverse. And these two quantities will be equal. Now notice K1 is not necessarily equal to K minus 1. K1 is only equal to K minus 1 if the concentration of A is equal to the concentration of B when equilibrium is actually achieved. So normally K1 is not the same as K minus 1. Now, what exactly is the meaning of K? What exactly is the meaning of the rate constant? Well, the rate constant is given by the following equation known as the Arrhenius equation. And this Arrhenius equation describes what the rate constant actually symbolizes. So the rate constant K is equal to the product of the frequency factor A and e to the power of negative EA divided by RT, where R is the gas constant, T is the absolute temperature, EA is our activation energy. So right away, because the activation energy appears in this Arrhenius equation, that means changing the activation energy changes the value of K. And so when an enzyme acts on a chemical reaction, it affects the K value. And that makes sense because we know that enzymes do not affect the concentrations of reactants or products. And so if enzymes increase the rate of the reaction and they cannot increase the A value or B, that means they have to increase the K value, the rate constant. So if we look at the Arrhenius equation, we see that if we decrease the value of EA, so remember enzymes, they stabilize the energy of the transition state, decreasing the energy of the transition state, and that decreases the free energy of activation. And so when enzymes decrease the activation energy EA, they essentially decrease this entire exponent. And since the exponent is negative, what that means is this entire quantity will increase. And so by decreasing the activation energy, our enzyme increases the rate constant, and that's precisely what increases the rate of that reaction. So remember, inside our body, the temperature remains constant. The core temperature is about 37 degrees Celsius, and that means all the reactions taking place inside our body take place at a constant temperature. So the temperature remains constant. And what that means is the enzymes have to affect the EA to actually change the K to increase the rate of that particular reaction. Now, what about A? Well, A is known as the frequency factor, and this basically describes the frequency of collision between the reactants. Remember, according to the collision theory, for a reaction to actually take place, those reactants have to collide with a great enough energy. Now, this collision frequency is described by A, and we know if the collisions are more frequent, then it is more likely that we're going to produce the products. And so if the frequency of collision increases, the A value increases and the K will also increase. Now, does the enzyme affect A? Well, remember, the enzyme places the substrate inside the active site, and what that does is it creates a microenvironment, and it basically decreases the space in which the reactants are colliding. And if the space is smaller, the collision between the reactants will be much more likely. And so enzymes can also actually increase A because they decrease the space in which the reactants are actually allowed to move. And so if the reactants basically collide more, the A value increases. So we see that enzymes predominantly affect the EA, but they can also affect A. They can decrease EA and increase A, and in both cases, we basically increase the value of K. So enzymes affect the rate constant, they increase the rate constant, and so that in turn increases the rate of that reaction inside the rate law. So enzymes affect the rate constant and in turn affect the rate law. So if we take a look at the following elementary reaction in which we take A and produce B, where K is the rate constant, we see that this is our rate law, and when an enzyme is added into the mixture, the enzyme will increase K, it will not affect the concentration of A. And so to increase V, the rate of that reaction, the enzyme must increase the value of K. Now, what exactly is the order of the reaction? So earlier we said that the order of this reaction was 1 and the order of this reaction was also 1, and the same thing was true for this particular case. So we see that the order of the reaction basically describes the rate of the reaction and how it actually depends on the concentration of those reactants. So let's begin with the first order reaction that we basically described in this lecture. So when a reaction's rate is directly proportional to the concentration of the reactant, it is said to be first order with respect to that reactant. So in this particular case, because the exponent is 1, this is a first order reaction, and that means the rate law, or the rate of that particular reaction, is directly proportional to the concentration. So by doubling the concentration of A, we double the rate. By quadrupling it, we quadruple the rate. By tripling it, we triple the rate, and so forth. So if we have a direct correlation between the reactant concentration and the rate of the reaction, then that means that reactant is first order with respect to that particular reactant. Now, to calculate the overall order of that particular reaction, we have to sum up all the exponents in that particular chemical rate law. And so because in this particular case we only have one exponent, that means the order is first. And in this particular case, the order is also first. But if we, for example, move on to a second order reaction, let's suppose we have A and B are the two reactants and they react to produce C. And this K value is basically the reaction constant, the rate constant. Now, if A is first order and B is also first order, then this will be our rate law. So the rate of the reaction V is equal to K, that rate constant, multiplied by the concentration of A to the power of 1 and the concentration of B to the power of 1. And the overall order of this reaction is 1 plus 1, so we simply sum up the exponents, and that gives us 2. And what that means is, by doubling A, we double V as long as everything else remains constant. Likewise, if we double B while A and K is constant, V will also double. But if we double A and B while K is constant, we quadruple that V value. And so that's what it means for a reaction to actually be second order. Now, we can also have a slightly different second order reaction. So in this case, we have two reactants. But what if we have a single reactant? So let's suppose we have A, and A basically converts to form B. And let's suppose that we have 2 moles of A produces 1 mole of B, and this is an elementary reaction. So this is the K value, the rate constant, and so in this case, the rate law, V, is equal to K multiplied by the concentration of A. But because this is an elementary reaction and the coefficient is 2, what that means is we'll have a coefficient of 2 on top of that A. So this reaction is second order with respect to K, and with respect to A, and the overall order is also second order. So this reaction and this reaction, they're both second order. The only difference is we have a single reactant here, but we have 2 reactants here. In this particular case, if we double A, then we quadruple the velocity because 2 to the power of 2 gives us 4. But in this case, by doubling A, we essentially double V if everything else is kept constant. But if we double A and B and we keep K constant, then we quadruple the value of V. And finally, we can also have 0th order. And in the 0th order, basically the concentration of the reactant has no effect on the rate of that reaction. So if a reaction is 0th order with respect to some reactant, then the rate is independent of that reactant's concentration. For instance, if we have A and A is transformed into B and K is the rate constant, and we know that A is 0th order, what that basically means is the exponent will be 0, this will become 1, and so the rate law is V is equal to K. And notice that changing A, either increasing or decreasing, will not affect the value of V. And some enzyme catalyzed reactions inside our body are in fact 0th order. And what that means is, by changing the concentration of A, that will not affect that rate of the reaction. Now, we can also have something known as a pseudo-first order reaction. And a pseudo-first order reaction is actually a second order reaction that behaves like it's a first order reaction. Now, what's one example of such a reaction? Well, let's suppose we have a second order reaction as shown, but the concentration of A is very, very tiny, but the concentration of B is very, very high. Now, in this particular case, even though it's a second order reaction, it will behave like a first